Welcome, everyone. Today we're doing a deep dive into agent memory, what it is, why it matters, and how modern AI agents actually use it. Over the last couple of years, large language models have evolved from stateless text generators into systems that can plan, use tools, and act over time. Once you cross that line into agents, memory stops being a nice-to-have and becomes a core capability. Here's the intuition. If you talk to a chatbot that forgets what you said 5 minutes ago, it feels broken. If you deploy an engineering agent that can't remember your repo conventions from last week, it will keep repeating mistakes. And if you ask a research agent to run a multi-day investigation, it must track hypotheses, evidence, and decisions across many steps. A big context window helps, but it's not enough, because long logs are noisy, redundant, and expensive to process. What we need is selective, structured memory. Before we go further, let's clarify terminology, because these ideas often get mixed up. Agent memory is a persistent, self-evolving memory state that the agent can deliberately write to and retrieve from over time. That's different from LLM internal memory work, which focuses on model mechanics like KV cache, long context architectures, or attention efficiency. It's also different from classic RAG, which is often a mostly static knowledge lookup. And it's different from context engineering, which is about temporary prompt and context management. Agent memory is uniquely about an evolving cognitive state that supports adaptation. Here's how we'll organize the topic. First, forms. What carries memory? Second, functions. Why do agents need memory, and what roles does it serve? Third, dynamics. How does memory get formed, refined over time, and retrieved at the right moment? By the end, you'll be able to look at any agent system and quickly identify what kind of memory it uses, what it's for, and how it changes over time. Let's start with forms, what carries memory. In practice, agent memory shows up in three major forms: token-level memory, parametric memory, and latent memory. Each form has a different trade-off in transparency, editability, cost, and generalization. First, token-level memory. This is the most common form in real systems. It stores memory as explicit, discrete units that you can inspect and edit. Text notes, dialogue snippets, extracted facts, tool outputs, even visual tokens. Token-level memory can also be organized by structure. Flat memory is like a list of chunks or episodes. Planar memory uses a single-layer structure, like a graph or a tree, to encode relationships. Hierarchical memory uses multiple layers, allowing abstraction across levels, like raw documents at the bottom and distilled insights at the top. A simple example: imagine a personal assistant agent. Flat memory might store every preference as a bullet list. Planar memory could connect preferences to contexts, like linking likes dark mode to mobile apps and work laptop. Hierarchical memory might store raw chat logs, then summaries, then a stable profile. The key is that token-level memory is transparent. You can deduplicate, resolve conflicts, and directly audit what the agent believes. Now, the other two forms. Parametric memory stores knowledge inside model weights. It can make behaviors feel like instinct, but it's harder to edit and audit, and it usually requires training or fine-tuning. Latent memory sits in continuous internal representations, like learned memory tokens, embeddings, or reusable hidden states, sometimes persisting across steps. Latent forms can be compact and machine-friendly, but they can also be less interpretable. In practice, many systems combine forms: token-level memory for auditability and latent or parametric mechanisms for efficiency and generalization. Next, functions. Memory is not one monolithic thing. It's a set of distinct capabilities. It helps to separate memory by what it is for, not just by time horizon. At the highest level, there's long-term memory across sessions and short-term memory within a session. Functionally, we'll use three pillars: factual memory, experiential memory, and working memory. Factual memory answers: what does the agent know? It stores declarative facts about users and environments. In human terms, it spans episodic traces and semantic knowledge. In agents, this often starts as logs of interactions, then becomes summaries, extracted entities, and stable facts in a vector store, a key-value database, or a knowledge graph. The functional goal is consistency, coherence, and adaptability. For example, a support agent remembers your product plan, your preferred tone, and what troubleshooting steps already failed. Experiential memory answers: how does the agent improve? This is procedural and strategic knowledge distilled from past trajectories. Think of reusable workflows, planning templates, tool use strategies, or lessons learned from failures. A coding agent might store a debugging playbook, reproduce the bug, isolate the failing module, add a minimal test, fix, and verify. A web browsing agent might store an effective search and verify routine. Experiential memory is where continual learning and self-evolution show up in practice. Working memory answers. What is the agent thinking about now? It's the active, capacity-limited workspace used during a task. It might be a scratch pad, a plan, an evolving checklist, or a set of retrieved facts that are currently relevant. A useful way to think about the overall system is a cognitive loop. Encode outcomes into long-term memory, retrieve what matters for the current situation, and process it inside working memory to choose the next action. Now, dynamics, how memory operates and evolves. A useful way to think about the life cycle is three core processes: formation, evolution, and retrieval. This is the shift from memory as static storage to memory as an active management system. Memory formation is how raw experience becomes compact memory. There are 5 common formation operations. 1. Semantic summarization, compressing long logs into concise summaries. 2. Knowledge distillation, extracting reusable facts or strategies. 3. Structured construction, turning unstructured text into graphs or hierarchies. 4. Latent representation, encoding experiences directly into embeddings or machine-native states. And 5. Parametric internalization, pushing memory into weights through updates. Memory evolution is what keeps a memory base usable over time. If you only append, you eventually get contradictions and clutter. Evolution includes consolidation, where related entries are merged, updating, where stale facts are revised, and forgetting or pruning, where low-utility information is discarded. A simple example is user preference drift. An agent may have memorized that you like concise answers, but after repeated feedback, it should update that preference rather than accumulating conflicting records. Finally, memory retrieval. Retrieval is not just nearest neighbor search, it's task-aware selection. The system must construct a query conditioned on the current observation and task, pick which memory module to consult, and decide what format to return: raw snippets, structured facts, or a concise summary. If retrieval is noisy, it can hurt performance by distracting the model. If it's too strict, it may miss key evidence. Good retrieval is what makes memory actually useful at decision time. Let's wrap up. A unified way to think about agent memory is forms, functions, and dynamics. Forms tells you what carries memory, functions tells you why it exists, and dynamics tells you how it is formed, refined, and used. This framing helps you compare very different systems under one language. Looking ahead, there are frontiers that matter if you're building agents today. Automation-oriented memory design, deeper integration between reinforcement learning and memory, multimodal memory that stores images and audio alongside text, shared memory for multi-agent systems, and trustworthiness concerns like privacy, safety, and conflict handling. The takeaway is that memory is becoming a first-class primitive in agent design. If you enjoyed this breakdown, like and subscribe. And if you're building an agent, try applying this lens. Identify the memory form you're using, clarify the function you need, and then design the dynamics carefully so memory stays coherent as it grows. Thanks for watching, and check the description for links and resources.